Rain, can I start?
You're all set.
Okay, cool. Yeah, thanks, Kadaga, for the introduction. Thanks for everybody joining in person, also joining online. So it's actually my first in-person seminar. We just talked about it. It's after 2 years. So that's kind of cool. Right, so I'm going to present some part of my work that I've been doing the past 2 years here at AML, mostly focusing on one study that just came out a few weeks ago, that is with the title Modulation of Equatorial Currents and Tropical Instability Drives during the 2021 Atlantic window, but I will also provide some background information and some more information about a study we also did that led to this very new study. So, and I also would like to acknowledge, first of all, my advisors, Renatus Perez and Greg Foltz here at AML, and then also Peter Brandt, Ajit, Sankili, Rick Lumpkin, and Rebecca Hommels, who contributed to this recent study. For those of you who are not so familiar with tropical instability waves, I thought it would be good to provide a short history about the research that was done on tropical instability waves over the last 50 years by now. So it all started with the Atlantic Tropical Experiment, the GATE program, where they noted sort of meandering equatorial currents, temperature, and salinity based on shipboard observations and moving observations. They didn't name them tropical instability waves, so that came later. But at that time, I mean, what they observed were tropical instability waves, but they were just mentioning or naming them meandering of currents. So shortly after that, satellite observations emerged and confirmed the existence of these long waves in not only the Atlantic Ocean, but also the Pacific Ocean. And that started a whole lot of studies, both based on idealized model simulations, but also observations using the GATE observations, working on the generation mechanism of these instability waves. And it became more or less clear that the instability of the equatorial currents was the favorable generation mechanism for tropical instability waves. This is why the name evolved, tropical instability wave. So then in the beginning of the 90s, a dedicated experiment took place, the 1-year tropical instability wave experiment in the Pacific Ocean from 1990 to 1999, providing a lot of new insights on the kinematics of tropical instability waves. And at around the same time, mooring arrays, first of all, developed in the Pacific Ocean, the Tau array, and then in the late 90s, also in the Atlantic, the Pirata arrays. So these were important to provide, first of all, sustained time series, so continuous measurements of also subsurface parameters, but also providing velocity measurements, which are not really available from satellite observations. So with these longer time series, more studies focus on longer time scale variability of tropical instability waves related to ENSO in the Pacific, or to the Atlantic zonal mode, for example, in the Atlantic Ocean. And then most recently became more and more recognized that these instability waves also have an impact on biogeochemical variability. So for example, on oxygen, on nutrients, and chlorophyll. Okay, so same figure I showed in the beginning. Just want to mention the mean characteristics of tropical instability waves in the Atlantic that we know by now from all these studies. So shown here is just a snapshot of SST data for 1 day in August last year. We can see nicely the equatorial cold tongue here in these blue or green colors, the colder waters expanding into the central Atlantic, and then these cusp-like features at the northern edge of the cold tongue, which are the tropical instability wave signature in SST. So the mean characteristics, so they have a zonal wavelength of about 600 to 1200 kilometers. They overall propagate westward with about 20 to 50 centimeters per second, which means that at one specific location, these oscillations have a period of about 15 to 40 days. So this is more or less what I will be using as the intraseasonal timescale. This propagation is a bit more clearer when we look at this loop of daily SST from the summer of 2022, so starting in June and ending in about September. So what happens in the beginning of summer is that the intensifying winds, they cause more colder waters expanding into the Atlantic, Central Atlantic, which is then called the equatorial cold tongue. And along the northern edge, especially, you can see these wave-like features developing, which are again the signature of SST, the signature of TIWs in SST. Most pronounced, as I mentioned, north of the equator, where we have the strongest gradients, but also to some extent south of the equator at the southern edge of the equatorial cold zone. What we also know from satellite observations is the location and the favorable or the most dominant periods of these instability waves, which differs a bit depending on the variable that we look at. So, for example, in this study here by Ati and Marat from 2008, they looked at variance spectra for SST on the left side here and for SLA on the right side at different latitudinal bands, and then over the longitudinal range of the central equatorial Atlantic, or almost the whole Atlantic, the whole equatorial Atlantic is. So what we take from this picture is basically that at 2 north, this is where we see the highest variability due to tropical instability waves west of 10 west. So this 10 west is more or less the magical longitude. West of 10 west, we have tropical instability waves. What we see east of 10 west, especially on the equator, more or less higher frequent variability, and also non-propagating features. So these are more associated with sort of free equatorial waves in the eastern part of the Atlantic. For sea surface height, we see the highest variability also west of 10 west and a bit further north at 5 north. So we can see this even more clearer in the map of standard deviation for SLA and SST. So SST peaks around 1 to 2 degrees north, where we have the strongest meridional SST gradients. And for sea surface height or sea level anomaly, we have a peak at around 5 north. So there are still, of course, instability waves on the equator, but they don't show up in SLA because they are mostly associated with equatorial I waves that don't have any signature in sea surface height. Whereas these instability waves at 5 north, they resemble Osprey waves, which again, of course, have a signature in SSH, which we observe here in this figure. From the moving observations, we can, as I mentioned, also get more insights on the subsurface parameters and also on the longer term time series. So, for example, a few years ago, we looked at the kinetic energy on the equator due to tropical instability waves, where we have about 20 years of measurements, and where we can see a pronounced seasonal cycle, first of all, but also we can see, the red curve is just a repeating seasonal cycle. And then in the black line, we see the actual time series, which shows quite some pronounced year-to-year variability, sometimes exceeding the seasonal cycle, but then also much weaker than the seasonal cycle. So some pronounced antenna variability that we can see in moving observations. We then recently also looked at the vertical structure of tropical instability waves, which we can nicely do with the remote observations. So in a study by Van Hooijkamp, almost 2 years ago, we just derived northward phase and southward phase composites of the tropical instability waves, which are, so by default, these two phases are more or less symmetric. That's what you can see. They extend to something like 100 meters, and they maximize between 20 to 40 meters. So these symmetric phases are then disturbed by cross-equatorial winds. So here we calculated the influence of the winds, or we excluded the influence of the winds, because the winds, or the meridional part of the equatorial winds, that is inducing some shallow overturning circulation across the equator. That's the so-called equatorial roll. And that is, again, inducing some asymmetry to these northward and southward phases, inducing shear and inducing mixing. So in the end product, that's different from just the very symmetric structure of tropical instability waves. Just a few more words on the seasonality. So in general, what we see from mode velocity observations here on the left side, but also from also from satellite observations, focusing on sea surface salinity, sea surface temperature, and sea surface height. We see, first of all, intensification towards summertime, mostly pronounced between June, July, August, and September, depending a bit on the variable. But overall, a very pronounced annual intensification. There are sometimes or some years with pronounced winter TLWs that is causing some slight semi-annual cycle, but overall the annual cycle dominates. Right, these are the satellite observations. Again, just showing the intensification of sea surface salinity, sea surface temperature, and sea level anomaly in the fall summer. One big motivation why we care about tropical instability waves is their impact on the heat budget. So this figure is taken from the Pacific Ocean, but it's the very similar situation in the Atlantic Ocean. So red colors here mean that TRWs cause warming, and blue colors mean that TRWs mean or they cause cooling in these regions. So on the equator, instability waves, they induce warming just by transporting warm equatorial waters towards the equator, and then the other way around, they attract the cold waters on the equator away to the off-equatorial regions north and south of the equator. So they have an impact on the regional heat budget. Then besides advection, they also have an impact through vertical shear and vertical mixing. So this is here taken from a study by Jim Moon. About 15 years ago, it was thought that instability waves have a very huge impact on the mixing. So this figure here shows a few different sections or a few different locations in the Atlantic and in the Pacific Ocean. But this gray curve here, that's the the mixing curve or the mixing profile that these authors observed in the Pacific Ocean in 2008. So huge, almost the magnitude of an order of magnitude larger than anything that they observed with long-term observations. So they thought these instability waves have a huge impact, but by now they just published in their paper 2022. They are a bit more conservative and think, because they've never again observed these high values, so they are more or less thinking there's still a significant impact of these instability waves on mixing, but just not as strong as they would have thought based on these 2008 measurements. And then also instability waves have an impact on the atmosphere. They impact winds, precipitation. They can also impact the location of the ITZ just through their impact on the SST pattern. Okay, and then lastly, away from the surface and the subsurface, we also showed that strong instability waves have an impact on the deep ocean. So these instability waves at the surface, these kind of forced waves, they excite free equatorial waves that then propagate part of the energy downward as their Nye waves. And you can see here just schematically the propagation pathways with the beams, the energy beams of these Nye waves. So it takes about 9 months, 270 days, if you have instability waves exciting Nye waves in the western part of the Atlantic before they reach the deep ocean, or the very deep ocean in this case. We also, so that was based on theoretical pathways. We also did, almost 5 years ago, we did a cruise crossing the whole equatorial Atlantic, where we could show these waves in a trans-equatorial section here of melting velocity. That's the upper left figure. And then we also used some high vertical resolution model simulations to see if we can reproduce these patterns of intraseasonal wave propagation, which we can do for certain years. But then there are also different sources of intraseasonal variability, like the deep western boundary current. So instability waves at the surface are just one source for deep equatorial intraseasonal variability. So why we care about these deep intraseasonal variability is because at depth, this kind of energy is providing the energy for maintaining deep equatorial circulation. So, for example, the equatorial deep jets feed from deep intraseasonal variability through the momentum flux conversions. So at depth, this is why we care also in the deep ocean about instability waves at the surface. Okay, so just a brief summary why we care about these instability waves. I mentioned we can observe them in almost every variable that you can think of. At intraseasonal timescales, they are really dominant signal in the central equatorial Atlantic. They are very pronounced during the summer, and some years also in the winter time. We discussed the role of instability waves on the heat budget and the freshwater budget, both through advection and through mixing. Their impact on the atmosphere, and then also their role for the deep ocean. Why I cared about the instability waves based almost like 2 or 3 years ago is based on some papers that came out around that time. So these, it's 4 different papers. They were all discussing either if the whole global mean circulation has accelerated, or just different parts of the equatorial circulation like this paper, but they all have in common that they found some acceleration or intensification of these currents. And we thought one step further, what would it mean for the instability waves if the ocean is actually speeding up? And we can look at the mean zonal surface flow in the Atlantic to just think about the consequences. So the main current branches in the equatorial Atlantic are the westward branches of the South Equatorial Current, so the northern SEC and the central SEC around the equator, and then also the eastward flowing North Equatorial Countercurrent. So especially in between the NECC and the NSEC, we have a region of strong meridional share of zonal velocity. And in this region, the instability waves, they really feed off this meridional share. And if we just think about an acceleration of these currents, you can see how both the meridional velocity gradient, or the meridional gradient of the zonal velocity, but also the vertical gradient of zonal velocity would increase. And this would then again, or in turn, mean that the tropical instability wave activity would also increase. So that was our starting hypothesis, and that's what we also discussed that's what we tried to answer in a study that came out about 1 year ago that I will just briefly summarize before coming to the main paper. The data I've used for both studies actually is based on satellite observations of SST, SLA, seafloor salinity, and chlorophyll. I'm also using reanalysis data of wind speed from Arrow 5. Then I'm using near surface velocity, so approximated at a depth of 50 meters from a synthesis product that is based on drift observations, reanalysis winds, and satellite depthymetry, and that is maintained by Rick Lumpkin. And then also I use the Mote Observatory on the equator at 20 degrees west that's providing upper ocean velocity since more than 20 years by now. And then it's also maybe useful to briefly define what I mean with tropical instability wave activity, because I will be using that term quite a lot. So we can think of any of the gridded variables like SST, for example, which are provided as a function of longitude, latitude, and time. So P is just here a placeholder for any gridded variable. And what we do to these time series at each grid point is we apply a temporal filter. So we are isolating the interseasonal part of the time series, 20 to 50 days. And then in the next step, we also isolate the tropical instability wave spatial scale that we know from all the previous studies. So we're applying 4 to 20 degrees zonal wavelength. We're ignoring shorter spatial scales and also longer spatial scales, which are almost spacing scale at that point. So we apply these two filters, and I took here just a snapshot of SST to show what the filter actually looked like. So on the top, this is just an SST snapshot during the summertime, where you don't really see much of a TAW signal. You can, maybe if you know where they are, you can see them, but not so much really before applying the temporal filter that already isolates these oscillating waves, all these oscillations north of the equator quite well. And then the zonal filter is even more reducing the noise, mostly of the equator, but also helping to isolate the signal. So this is what the filter does. We then have this daily filter time series where we use 1 month of data to calculate standard deviation, just to have a measure for the waviness, if you like, or for the oscillations. And this already gives us the monthly time series of our TAW activity index. And then we are using sometimes spatial averages, sometimes seasonal averages, but I will mention that, and you will see that also in the figures. But they are all based on the same TAW activity index for the individual parameters. Okay, so just briefly summarizing the paper that we did about 1 year ago on the intensification of Atlantic tropical instability waves. So first of all, we defined where and when we see the highest variability due to TAWs, to also in the end see if we have just a spatial shift or temporal shift of the activity when we look at the trends. So it's for SST on the top, SLA in the middle panel, and then meridional velocity at 50 meters on the bottom. For all these parameters, we see most activity between 30 rest and 10 rest. SST, also as known from other studies, peaking slightly north of the equator, whereas SLA and meridional velocity, they peak further north at around 4 to 5 north. What's also worth mentioning here is that we would expect usually also an elevated band of meridional velocity variability near the equator, which we don't see in the product. So that really indicates that this product is underestimating these high frequency velocity fluctuations on the equator. So we are mostly focusing north of the equator when we're looking at this product. Right, and then the timing of the activity, they all peak in July, but then overall the June to August season, that's where we have the overall peak of tropical instability wave activity in these parameters. And then the trends, just again for the same 3 parameters. So whenever you see red colors, that means an increase in activity. Blue colors mean a decrease in activity. For SST, we see a very pronounced increase, just where we also see the mean characteristics. So very pronounced, very significant increase. SLA is more or less a moderate increase, and meridional velocity is more or less a weak increase overall. We can also see that the timing of the increase is during the time that they usually peak. So in June, July, August for SST, and then May, June, July, maybe a slight shift to an early onset in SLA and meridional velocity. And again, not very significant for meridional velocity, but for SST, it looks quite nice. The overall time series of when we're using these marked months here in the box, or the values in the rectangular box here, that gives us an annual TRW activity value. We see in the SST parameter a very nice and steady increase, which is not so pronounced for the other variables. Overall, we end up with an increase of more than 40% for SST variability, 26% for SLA, and just 4% when looking at meridional velocity. When I started this analysis, I didn't have all the data for 2021. So as you can see, this 2021 year, that is one of the lowest activity years, and it was a bit disappointing to include them. Before that, I had some really nice, you see the difference, especially for meridional velocity and sea level anomaly, the increases were much higher. So at that time, a bit disappointing, but then in the end, that led to us, that led to some motivation for looking into this specific year. And this is what the most recent study is focusing on. Just a few words, because it will be important also for the recent study on the generation of tropical instability waves. I didn't mention why or how they are generated, or not so much in the beginning, because I'm doing it now. It's best to look at the average or the temporal average of the eddy kinetic energy budget, and I'm not going to go into too much detail, but just mentioning the most important terms that we can use to investigate the reason for the intensification of tropical instability waves. So on the left side, we have the advective terms. Those only cause a redistribution of eddy kinetic energy, so not really a source. Then we have the dissipative terms that act as sinks. The third term here, that's the so-called eddy pressure flux. So that's basically describing how energy is radiated due to equatorial waves in this case, or due to waves in general. So that has been mostly neglected in previous studies. We can also not really calculate that from observations, but it's a fair assumption to exclude them at this point. And then we're focusing on these two terms, which are the energy conversion terms. On the one side, the baroclinic energy conversion. So that is describing how available potential energy is converted into eddy kinetic energy. And then the barotropic energy conversion term, that is describing how mean kinetic energy is converted into eddy kinetic energy. And it consists of an eddy term and also the meridional velocity, the meridional gradient of zonal velocity term. Okay, it might be a fair assumption to only focus on the barotropic energy conversion term. Again, we cannot look at the baroclinic energy conversion term because we don't have the needed vertical velocity fluctuations from observations. But in a study, or in a model study by von Schuckmann et al. In 2008, they specifically investigated the difference between barotropic and baroclinic energy conversion. So the blue colors here mean that we have a transfer of mean kinetic energy into the eddy kinetic energy or into the fluctuations. So that means the TRWs are feeding, or they're growing in this season. And we can see from this figure, most of all, we have these two bands of barotropic energy conversion in between the main currents that we just saw also a few slides ago. And we also have the seasonal intensification. We have the strongest energy conversion in July and September. For baroclinic energy conversion, we also see a seasonal cycle, but to a lesser degree, and also not as strong as barotropic energy conversion. So these maps are based on upper 50-meter averages. When we're looking at the vertical and latitudinal direction, we can also see that the baroclinic energy conversion here doesn't reach as far deep as barotropic energy conversion, and especially north of the equator, in this area between the NSEC and the NECC, it is really the barotropic energy conversion term that dominates, whereas the baroclinic energy conversion term might contribute to TRW generation closer to the equator. Right. So what we did, we looked at the near surface velocity product from the near surface velocities from the drifter synthesis product. This is only estimated one specific depth, but that's the best we can do with the observations. Okay, and that's shown here on the top right, the barotropic energy conversion at 50 meters depth for June and July, which is the peak of this term. So we do not see a secondary band like we did in the model studies. Again, this might be due to an underestimation of the velocity variations near the equator. So we again focus more on this north equatorial section region. Right. Overall, this term also shows a nice increase, which you can see here in the second panel. And then we went on and tried to find out which component of the overall conversion term is responsible for the overall increase of energy conversion. So our starting hypothesis was that the currents intensify. If the currents intensify, you would see an increase in the meridional share of tunnel velocity, which we don't see. We don't see that at all. Instead, we see that the eddy term is the one that is driving the overall increase. And that might be a bit counterintuitive at first. And we thought about possible reasons for that. It could be that, for example, the equatorial currents are so close to instability that any increase of the currents would not be measurable as an increase in the mean velocities, but they would rather project automatically or directly into the fluctuations. So that could be one possibility. But yeah, it was more or less a more surprising result than we thought. So we found a nice intensification, but maybe not for the reason that we thought in the beginning. Okay, and then one impact of this intensification on the temperature detection was that the overall pattern of cooling of the equator and warming on the equator is intensified by more than 74% actually. So quite a huge increase over the last about 30 years. But again, it's important to note that, especially on the equator, horizontal advection due to TRWs causes a warming, but then causes also cooling due to mixing. So on the equator, it's an opposing or contrasting mechanisms or contrasting signs, but off the equator, they have the same sign. Advection and mixing both cool off the equator. So yeah, that's why we just discussed before with Kantaga. This is why it's not really clear which process really outweighs the other on the equator, mixing or advection. Okay, just to conclude this first study, we have this intensification over the last 3 to 4 decades in almost all variables that we observed. I didn't even mention the mood observations and sea surface salinity, but we also see that. The intensification is due to intensified high frequency current velocity variability, not so much due to meridional shear. And the eddy advection pattern has increased by more than 70% over these last 3 decades. Okay, And this led, especially when you look at the abstract, I did look at the abstract of the first paper again, and the very last sentence is actually very close to what the title of the new study developed into, without me knowing it. But when I read it again, I thought that sounds very familiar. So that's actually, yeah, very much the title of that paper. And we're very focused now on this very specific year where we saw this drop in activity. And this paper just came out just a few weeks ago, at the beginning of the year. Okay, so just a bit of background information on this 2021 Atlantic El Niño. So in the summer of 2021, the Equatorial Atlantic that experienced SST anomalies of more than 1 degree in some parts, when you look at the daily data, even reaching up to 2 degrees over summer, but then also expanding also in the boreal autumn. We see that a strong downward in Kelvin wave in the sea surface height data propagated during the month of May, mostly from the western boundary to the eastern boundary. And this is also aligns with zonal wind source anomaly, or these westerly wind bursts that we see in early May. But these wind bursts, they don't explain really why, or the western boundary origin, because the wind bursts are more focused on the central Atlantic. So I'm going to talk about this a bit more on the next slide. And then what we see in 2021 is also a huge impact on chlorophyll concentration. So in fact, in the summertime, the chlorophyll concentration dropped to the lowest values since the beginning of satellite observations. And then in the wintertime, this bloom here is also again the strongest values for any wintertime chlorophyll concentration in this area, in the Equatorial Atlantic. So overall, quite an outstanding event. So we then had a study last year led by Sanki Lee, focusing on the genesis of the Atlantic El Niño. Again, was showing that this event was the strongest in more than 50 years of SST observations. And the short story is that it's actually not just the wind burst, but also a combination of wave reflection at the western boundary, and these Rossby waves reflecting into Kelvin waves at the western boundary, and then this Kelvin wave is being amplified or reinforced by the westerly wind bursts in the central basin. And in fact, the wind bursts are more or less related to the MJO in the Atlantic, but this was more or less the focus of that study led by Sanki. So we wanted to focus on the impact on the currents of this event and on the tropical waves. So first of all, here shown is the impact on the zonal velocity in the month of May 2021. Again, on top, that's very familiar, looking to one of the first slides, just showing the mean circulation or the mean zonal surface flow in May over this almost 30-year-long time period. And then the anomaly in May 2021. So you can see huge eastward anomalies, meaning a reduction of the westward currents, which in fact almost cut them in half, which you can see here in the bottom panel. So average over this North Equatorial box, for the month of May, we see a huge reduction from about 30 centimeters per second to about 15 centimeters, so really cutting it in half. And then even beyond this propagation of the Kelvin wave during May, we still see some reduction that is then probably more associated with any wind forcing properly. Okay, so huge reduction of the westward currents. What about the meridional share of the zonal currents? So on average, we have these strong, I know the slide takes a bit before it's loading, so it will come up shortly. So on the left side, you can see the meridional share bands, mostly focusing between, or most pronounced between the NECC at 5 north and the NSCC between 1 to 2 north. And then also the other bands of meridional velocity, meridional share of zonal velocity for the south. In 2021, the anomalies showed not much signal on the equator. We do see some signal of reduction north of the equator at around 4 to 5 north, and also during the summertime. But overall, not much signal on the equator, which we would have expected also from previous model studies that showed a huge impact of Kelvin waves on the meridional share. So we don't see that really much. We then thought that one reason could be that the Kelvin wave, so these are just the structure function of the first three modes of Kelvin waves. That would just cause a uniform weakening, in this case, of westward currents, and and not really have an impact on the meridional share. So that could be one reason why we don't see much signal on the equator. We then look at the mooring observations at the equator on 23 So first of all, for the zonal velocity component, where you see in general the equatorial undercurrent going up and down over these 3 years, we see that the undercurrent was deeper than usual during the first half of 2021. So deeper undercurrent being further away from the westward currents that would reduce the vertical shear and also the eddy kinetic energy during these months when the undercurrent is deeper than usual. And then we also look at the meridional velocity. And the meridional velocity component is mostly used or mainly used to detect dropping instability waves. So you can see these wave-like structures in 2020, in 2022, but not much in 2021, not much at all. We also show here the dropping instability wave activity index based on meridional velocity. So you see this nice intensification in 2020, nice intensification in 2022, not so much intensification in 2021. So very weak TW season in 2021 based on velocity data. And not only on velocity data, we also look at SST, sea surface salinity, chlorophyll at 1 north, that's the upper panels, and then also at sea level anomaly at 4 north, which is shown here. So basically, we're just comparing the 2021 year with a climatological year based on all these different variables. And any blue colors mean a reduction of dropping instability wave activity, and red colors mean an intensification compared to the climatological cycle. So all these variables, they show a decrease in activity during May to more or less July. But then they also show some rebound activity in August. So overall, it was a weak season, but it was also a delayed onset. So a weak and delayed TW season based on these parameters. Again, we also look at the eddy temperature advection at 4 north, which, if you remember, dropping instability waves cause cooling at 4 north. But in 2021, that was almost reversed, that impact of dropping instability waves. So we looked at Pirata data at 4 north, where you have usually some kind of some small cooling in the summertime, but in 2021 there was a pronounced warming signal or positive anomaly in the upper ocean during the July to August, September values. And when we look at not only 2021 for these months and these step range, but for the whole time series, we can see how extraordinary this year was. So it was the strongest event since 2006, since the beginning of the time series. But again, it is not easy to say if it's just the dropping instability waves that causes this, but also heat fluxes and the vertical mixing must play a role. But then again, also mixing will also play in the same direction as the heat advection term. Okay, and then we looked at the barotropic energy conversion here at the bottom right now, which is also very reduced during the beginning of the season, which aligns with what we see from these other parameters. It's already indicating that barotropic energy conversion might have played a role in reducing this activity. Besides barotropic energy conversion, we cannot really, calculate baroclinic energy conversion. We can use the meridional SST gradient as a proxy, as a proxy for baroclinic instability. So we know from climatological values or from the climatological view that this Atlantic cold tongue, the equatorial cold tongue, develops in the summer, just north of the equator. So that's where we see the highest meridional SST gradients, peaking at around June, July, and at about 1 north. And in 2021, this meridional SST gradient was, of course, very much reduced due to the warming event, or the warm event on the equator. So reducing the SST gradients and reducing the potential for baroclinic instability. So therefore we think that it's a combination of reduced baroclinic and reduced barotropic energy conversion. Okay, and then very briefly, we looked also at the chlorophyll concentration during that year. So both from a seasonal point of view, but also from a TAW timescale point of view. And this is just the 5 last years at the mooring location at on the equator and 23 west. So what we see in 2021 are two things. On seasonal timescales, it was a very weak concentration, but on intra-season timescales, you can see these. We still have some pronounced fluctuations on these tropical instability wave timescales. And we were really wondering, because we just saw there's almost no signal in velocity due to tropical instability waves, why do we still see some kind of TW signal in chlorophyll data? And the reason we think this is possible is based on the meridional gradient of chlorophyll. So in general, the chlorophyll gradient is more symmetric about the equator. So the chlorophyll equatorial upwelling during summer causes a very symmetric chlorophyll front north and south of the equator, which you can see here on average. And in 2021, we see some slight reduction of this front of this meridional gradient. But then again, if you look at 2021 from a latitudinal perspective, which is here the red line, and the black line as the mean of all the years from 1998 to 2020. And then we look at one north, where TW-induced chlorophyll variability is strongest. It is not much different from the mean. So again, weak velocities, but still quite pronounced gradients. And we think this could be the reason why we still have this strong variability or these strong fluctuations in chlorophyll. So when we think of the equatorial Atlantic during summer, we have the equatorial cold tongue developing, we have upwelling in the equatorial Atlantic, and we have chlorophyll coming to the surface or closer to the surface, or also growing closer to the surface. In case of strong TW velocities, we have a strong advective loss also of chlorophyll. So the tropical instability waves, they act to transport the chlorophyll away from the equator, and this reduces the meridional gradients. But in case, like in 2021, in case of weak instability waves, we have less advective loss. So weaker velocities, the chlorophyll stays closer to the equator, and we have more or less the maintenance of the meridional gradient, or at least not the same level of reduction as we have in case of strong velocities. So we think therefore that there could be like a balancing mechanism between meridional gradients and velocities. Okay, and then very briefly, I'm not sure how much I'm doing on time, but just summarizing the results of this new study. So overall, the 2021 Atlantic El Niño was one of the strongest events in 50 years, and it also causes some very pronounced values in chlorophyll concentration. Also, again, since we have observations from satellites about 25 years ago. First of all, the westward currents, they were drastically reduced during May, but not so much impact on the meridional shear close to the equator. We see a very weak, but also a delayed tropical instability wave season in all the parameters that we looked at. And this is likely caused by a combination of barotropic and baroclinic energy conversion reduction. And then what we hypothesized in the end of the paper is that there's this kind of balancing mechanism between meridional gradients of chlorophyll and tropical instability wave velocities. So both components, they can partly compensate each other. Because if you think of, you need both ingredients to have variability. If you have no velocities, you can have the strongest gradients, but you don't change anything, you don't get any variability. And the other way around, if you have the strongest velocities, but there's no gradient, you don't change anything. You don't stir anything up. You don't create any TW-induced variability. So you need both to end up with some signal. Okay, and that's all I wanted to show. Thank you all for listening. Happy to answer any questions.
Yeah, great.